Right, gentlemen. Problems. Powering multiple load systems. So, if we're talking about major power systems, like the supply coming into some kind of factory or something, or an area, it's going to have multiple loads to that one load center. Okay, so problems where multiple real and reactive loads are all connected to one source can be solved simply by summing up all the individual real or the individual reactive components together and coming up with a total for that connection to that, in this case, 400 volt source. Yep. So you can add up all the powers in watts, add up all the kVARs, remembering that reactive inductive components are an addition, capacitive components are a subtraction, because they give reactive power back to the source, or is said to. So we add all the totals up, we come up with a total reactive and a total real power, and we can find out then the total apparent power using the power triangle. Okay, so we're going to go through this example. The way to look at this is to redraw that system with a single line power buses. So we don't need to draw the fact that it's got 3 lines. We can draw the source as being a single bus line, so 3-phase line at whatever voltage it is. And then we draw the loads with arrows pointing as either taking reactive power from the system, giving reactive power back here in terms of the capacitor, taking it there in terms of the inductor. Resistive loads will be a use of that real power. One there and one there. This is another inductor, L2, taking reactive power. Here's a capacitor giving some back. And then there's a motor that's going to take both real power and reactive power from that source. Okay, so I'm going to give you a set of these notes in a minute anyway. The system is redrawn, single line power buses and arrows to indicate the power flows. Please remember, inductors are said to draw reactive power from the system, i.e. they're a positive kVAR in terms of the system. Capacitors give it back, and negative kVARs. Motors draw both real power in kilowatts and reactive power in kVARs. So that's the system redrawn with the values from the original problem on the diagram. So we got 3.5 kVAR of inductor there, 9 kVARs being given back by C1, and 6 kilowatts for that resistor. Here's the motor. The motor's 13 kilowatts, and that draws 7 kVARs of reactive power as well. The magnetising current is what that's all around. Okay? Right, so we're going to have a look at doing that now, step by step. Okay? So I'm going to calculate the total reactive power drawn from the supply. So what we do is go Q total is equal to, we've got L1 is taken 3.5 kVARs. L2 is taken 3.2. Yeah, the motor is taken 7, and the capacitor 1 is given back 9, and capacitor 2 is given back 12. .5 and 3.2 is 6.7. Minus 7.3 kVAr. That's capacitive in nature, this load. Yeah.
So, we were talking last week about making your power factor by adding stuff.
Yeah.
If your overall factor was more capacitive, would you be able to add
Inductive. Yeah. So it would be unusual to end up with a system like this. What you don't want to be doing is crossing that line by adding either capacitance or inductance, because then you're in the realms of creating a resonance situation, which is not really a good idea. Okay. Mostly the load's going to be over inductive in nature. Just the numbers I picked here turn out to be capacitive. Yeah. Yeah. All right. So that's the total Q, minus 7.3 kVAr. Yep. What else can we calculate here? We can calculate P total. That is the power of R1, 2.5 kilowatts. The power associated with R2, 6 kilowatts, and the power associated with the motor, 13 kilowatts, equals 21.5 kilowatts. Yeah. Okay. Right, gents, so they're the calculations from the previous page. Total power is 21.5 kilowatts. Total reactive power is minus 7.3 kVArs. How can we calculate the apparent power, S, drawn from the supply by Pythagoras? So we draw the power triangle like so. We've got P here, which is equal to 21.5 kilowatts. We've got Q here, minus 7.3 kVAr. We want an OS. Yep. So you can get a lot from these trigonometry, triangular relationship here. So as Joe rightly says, S is equal to the square root of P squared plus Q squared. So it's the root of 21.5 squared plus minus 7.3 squared, and actually the negative sign is not particularly important here because it's going to come out positive anyway. The answer to that is No, it cannot be correct. .7 kVA. What does that leave us to find on my list of things to find? A line current drawn from the supply. Okay, so let's take that bit. How do we find a line current drawn from the supply? There's three ways of calculating power, isn't there? We've got S is equal to 22.7 kVA. Okay. So if you're unsure, let's get it from the units. Look. kVA. Yeah, or it's VA, which means volts times amps. So if S is equal to VA, yeah, I must be S over V, and actually I'm gonna, you led me down the wrong path there, Cootsy.
You just copied a lot, please. You copied your
amperage. Yeah. Alright. So the current, the line current, IL, always comes from S. Yeah. It's a complex current, isn't it? Yeah. It's got a real and imaginary part, but it's the 22700 over the 400 volts. You must remember that now we've got two different units. They've both got to be in the same multiple. Volts and amps, volts and VA here. So we can't, because unless we convert this to kilovolts, what will that come out as? 56.75 amperage. Okay. And the last thing that's asked them for is the power factor. Think of the triangle. You can get it from any one of the triangles. There's Q, P, and S, and the power factor is the cos of that angle. So therefore it is what? Yeah, it's the adjacent side, P, over the hypotenuse S, the power over the apparent power. Just remind me what the power was, gents, because it's on the other page. 21.5 kilowatts. Oh, and this is 22.7 kVA. Because they're both kilo, we can just use the numbers. And the answer to that is 0.95. So the cos of the angle, or the power factor, whatever you want to call it, is 0.95. What I look at now is this problem. Solving AC circuits using the power triangle method. We're going to look at this circuit and calculate the current in each circuit element, the voltage between the terminals 1 and 2. So we've been given the voltage between the terminals 1 and 3, but not the ones at the source, and the impedance presented at the terminals 1 and 3. Yeah, that's what we're going to look at doing. So, looking at that circuit, hang on, there it is. Looking at that circuit, what can we calculate? Have a look at it. What's the first thing do you think? Total resistance. Do we talk about resistance in AC circuits? Impedance. That's better. Okay. Is there anything immediately that we can calculate?
You can calculate your current and your impedance across the 60 volts.
Yeah, you can. In fact, immediately you can calculate two currents, can't you? Yeah. Which are? How do we calculate IR? Yeah, it's this B13. Yeah, that voltage, that's the voltage across it, isn't it? Over R. That's 60 volts over the 12 ohms equals. No, because they're in parallel, Keith. They've both got 60 volts across them. Remember? Back, two in parallel, voltages the same. Currents are different, voltages the same. Yeah? So it's 5 amps. Yeah? Okay. What about IC? It is. Tell me the values. Yeah, but it's E13 over XC, the capacitive reactance, which have been given in ohms. That's 60 volts over 5 ohms, which is 12 amperage.
Oh, right.
All right. What will that allow us to find, do you reckon? Yeah, we can get PR. How do I get that from what we've got now? You won't find the answer in there, Daniel.
PR power is your.
There's 3 ways to calculate power. What are they? I squared R, V times I, or V squared over R. Yeah. So in this case, we've got the voltage, we calculated the current, we got the resistance. We could use any one of them. So let's use E13 times IR. Yeah. So that's 60 volts times the 5 amps. What? 300 when I went to school. Wattage. I'll stop, Daniel. Don't worry. Alright, what else can we find? If we can find P, yeah, but that's more correctly called, Keith. What's the power term for the reactive component? Q, yeah. So we got QC, and that is equal to E13, same voltage, times IC. Yeah, it's 90 degrees out of phase with the power, but it can still be calculated using that formula. So it's the 60 volts times the 12 amps, which is 720 var. Yeah. Notice, no complex numbers involved yet. Okay. We love our complex numbers. Now what can we find? We could do, but you must remember that those two are out of phase with each other if you was going to do that. What, from these two powers, what could we find? Yeah, we can say that S we'll call it S31 because it's only, just going to clarify here, it's only the apparent power for those two components. It doesn't include that inductor yet. Alright? It's the apparent power seen by the 60 volts here. Yeah? How do I calculate that? Root of 300 squared plus 720 squared. I'm sure someone will push the buttons for us. Equals 780. Joe? 780. VA. Yep, correct. So, new page. We've got S is 780 VA. Yeah. If we think of that circuit just as it is, we've got a resistance Remind me what that R is. 12 ohms, won't it? Yeah, and we've got a capacitor, 5 ohms. Yeah, being supplied by 60 volts. Okay. That 60 volts is coming over here somewhere. Okay, and there's another component involved. But there's a series component in that line back there. Yeah, but what can we find now? Now that we know the total apparent power here is 750 VA and that's being supplied by 60 volts. Yeah, this is 3 and this is 1. Yeah, we can find the total current flowing IP, because S is equal to the voltage times IT. Yep, the line current, that is. IT must be S over V, which is 780 VA, over the 60 volts equals .13 amps. Yeah. So our original diagram now, we can bring back the inductor here. Three, 1, 2 and 1. What ohms is this? Just remind me. 8 ohms. Yeah, and we now know that we got 13 amps flowing there. So what does that mean we can do? Now we know that, because we also know that this is 60 volts. What can we do now? You can indeed. You can work out this voltage here. Yeah. VL. How do I calculate that, Daniel? The impedance, it's XL times IT. That is the 8 ohms times the 13 amps equals .104 volts. Yeah. Okay. What else can we find around that inductor? We can find QL, the reactive power associated with that inductor, can't we? How do we do that?
E1 by 2, or E12 times 5.
E12, what is it? E12 is that one. Yeah. we want this voltage here, don't we? VL times IT. Yeah, so that's the 104 volts times 13 equals 1352 var. Yeah. So now we got that, we can find the total reactive power, because that's the QL minus the QC, is it not? Yeah. It's 1352 minus 720, 632 var. There's only one power, but P total was 300 watts from earlier. We calculated that. So what can we find now? Yeah. S total is equal to 300 squared plus 632 squared (700 VA). Yeah. Now we know that, what else can we find? We could find the power factor. We weren't asked to find that. We want to know this. We know what total S is now. Yeah, because ST is equal to IT times E12. Yeah, it must be true that E12 is equal to ST over IT. That's 700 over 13 equals 53.8 volts. And therefore, can we get ZT? Total impedance comes from we could calculate it using series parallel impedance, but with all these other values, can we get it another way? Yep. E12, the line voltage we just calculated, over the line current, 53.8 divided by 13 equals 0. Alright, gents, so not a single complex number in sight. in that particular case, no need to use one. Alright? So there's, when you get these problems, you might be asked to do them a particular way, you might not. Okay? But it's a bit about knowing and being aware of, depending on what you're being given, being aware of the different ways you could tackle a problem.
What's the logic you get in the real world? It's like we change.
So, what we are going to do now is look at a problem involving power where we are going to use or need to use complex notation. We've got a series circuit of 45 ohms resistance, 28 ohms inductance, being supplied by a voltage source of 159 volts at an angle of 65 degrees. Yeah, so it's 65 degrees out of phase with the current. Voltage is 65 degrees out of phase with the current. Yeah. So it's a reference voltage. It's got an angle associated with it at 65 degrees. Don't forget, we haven't covered three-phase systems yet, but they consist of three voltages that are all 120 degrees out of phase with each other. So if you're looking at you'll have one phase that's at 0 degrees reference, but if you're talking about a different phase, it could have an angle of 120 degrees associated with it. Okay, so it's not unrealistic to have to consider that the voltage has got an angle associated with it. It's all about what we choose to be the component that's got 0 angle. Okay, so what we're going to look at with this problem is finding the magnitude and phase of the current I flowing through the circuit, the magnitude and phase of the voltage across the resistor and the reactance, and the active and reactive power associated with the resistor, the reactance and the source. Yep. Step by step. So, how could we go about doing that? Have a think. What's the common denominator of both components? What's the common thing to them? Sure? Both in ohms, yeah? Both got the same current. It's a series circuit. Yeah? RT, Joe? ZT? Yeah? So, what is ZT in this circuit then? It's 45 ohms, that is. Can we just add them two together? Can't just do, can you? 28, what is it? It's an inductor that's got a phase shift of 90 degrees. So we've got to write it like this. 45 plus 28 J ohms. No, the voltage has got a phase shift to 65 degrees. Now we're going to do now, we're going to want to be calculating I is V over ZT. Let's just correct that. EAB over ZT, that's what I labelled the diagram up as. So what forms, we've got a voltage in polar form, we've got an impedance in rectangular form. What would you prefer?
Both rectangles.
Would you? Okay then. That's rectangulars then. Yeah. So what we need then is we need EAB, which is equal to 159 angle 65 degrees. What is that in rectangular form? So we converted that to rectangular. Now we can do I is equal to EAB over ZT, which is 67.2 plus 144J over 45 plus 28J. So we've got to do the what will the bottom line be? Square both the numbers and add them together. Nice one, Keith. 45 squared plus 28 squared. 2000 what? $3,024 plus 144 times minus 28 must be negative. All over 2809. And the result of that is
1.076.
1.0 1.08 44J amps. Yep. Just in case we need it later in polar form, let's have that in polar form as well. What is it? So we've gone wrong somewhere. You admit we've gone wrong somewhere. How much have I got to rub out? Got to rub the last three lines out. What was this? So what you done then, Joe, was you multiplied that and you multiplied that and that, but you didn't do the full cross multiply. Yeah? I know I was wrong, right, because I'm comparing it with the solution I got in my notes, which I done by converting the impedance to polar, should get the same answer. Didn't knew we weren't going to get the same answer.
You knew.
So that's the top line. That's the bottom line. Bring those two constants together and the two J terms together. $7,056 minus. That's plus. You got a negative here. 6480 minus 1881. 4598. J all over 2809. Divide that out. 2.5 plus 1.63 J amps, and that in polar form 3 amps. Angle what? 33.9 degrees. That's better. Much better, because that's what I got more or less in here. Yeah. What you've got is you've got 144 times minus 28, right? But the J squared makes minus 1. So you've got a negative number multiplied by minus 1, strips the negative sign off it. Yep. Okay, that's why on the bottom line, even though one of these numbers is negative and the other one's positive, here, because we're multiplying by the complex conjugate on the bottom too, but the J squared cancels it out and you just end up the constant on the bottom. Yep. Okay, so you could have done the whole problem as well by converting the impedance to polar form and doing polar division as well. So either method would be correct. So, having done that, what can we now find about our circuit? We've found the magnitude and phase of a current I. Just remind me what that is in both forms, and I'll write it down here. 2.5 and in as 3 amps, angle 33.9 degrees. That's fair enough. So now we know the current flowing. What does that allow us to find? Magnitude and phase of the voltage across the resistor and the reactance. Can we do that now? Yeah? I think we can, can't we? What angle is associated with a resistor? So VR is the current. We can use the polar form, 3 angle 33.9 degrees. Yeah, multiplied by 45 angle 0 degrees. So this is polar multiplication now. Yep. How do we do that?
Times the thing, the angles.
Multiply the magnitudes, add the angles, yeah? So it's 3 times 45 is 135 volts. Angle, 33.9 degrees. VL, same current, 3, angle 33.9 degrees. This time we've got 28 ohms. Angle associated with the inductor, plus 90 degrees. Well done. So that's 3 times 28, 84 volts, angle 123.9 degrees. So you could equally do them with rectangular versions of the current and impedances. Still should get the same answer. All I would say is, if you can work with the polar ones, usually going to want the answer in polar form because it tells you how big the voltage is and what the phase angle is. Yeah, so even if you're working in rectangular, eventually at some point the final answer usually going to want it either in both forms because you want to use it later on, or the final answer in magnitude angle form. Alright? Yeah? Everyone happy with that? So, what else have we been asked to find about this circuit? The active and reactive power associated with the resistor, the reactance, and the source. Okay? Now, what we must do here is to calculate the power, we've got to consider, we've got to get rid of the angle involved. Okay? We've got this complex conjugate thing again here. Right? Remember, the power's only associated with the in phase part of the current. Alright? So let's hang on. So you have to use the complex conjugate, which effectively cancels out any angle. Okay? So what was our voltage? PR, okay, is VR times complex conjugate of I. That is, what was VR? Polar form. 135, angle 33.9 degrees. And we've got to multiply that by complex conjugate of I. That was 3 amps, angle. Yeah, we've got to change. Yeah. So we've got to do 135 times 3. Because you've got to take the conjugate of I, you've got to cancel the angles out. 405 watts, and the angle's 0 yet. Yep. QL is the voltage across it, which was angle 123.1, 123.9. You've got to multiply that by this complex conjugate of I, 3 angle minus 33.9 degrees. Yep. So 3 times 84, 252. Angle, what should the angle be? And it is 123, take away 33.9, 90 degrees. Yeah? All right? And then S must be EAB times that. That's 159 angle 65 times 3 angle minus 33.9 equals 477 VA angle Yep. All right. So always be prepared to use a mixture of polar and rectangular form in these problems. Try not to do too many conversions backwards and forwards. Otherwise you just keep reintroducing more and more error as you go through the problem. Yeah. Try and use the appropriate value at the appropriate time. Alright?